Welcome to a short tutorial on how to code backpropagation algorithm from scratch. Using the backpropagation algorithm, the artificial neural networks are trained. We are going to learn how to code backpropagation algorithm from scratch, meaning without using any library, just using Python. Trust me, it's not hard. Also, for you to be able to follow and understand this tutorial, you don't really require the understanding of advanced maths. If you're good with the high school maths, you will be able to understand this tutorial. The only prerequisite for this tutorial is the understanding of basics of Python. Wherever there is an advanced part required in Python, I will be teaching that part in Python. Also, please note that we will be learning the gradient descent algorithm also because that's required for the backpropagation algorithm's understanding. So let's jump in. All right, so let's get started. To get you started, you will need this notebook, the one that I'm showing on the screen right now. And how to get this notebook, either you can go to this particular repository that is there. You can just go to that URL and you will see something like this and you will find this notebook here. Or you could just check it out. Check it out as in you can use git clone and clone the repository to your home directory. Now this home directory can be anywhere where your Jupyter is installed. Okay, so in case you don't have the Jupyter environment, you can clone it in your CloudxLab environment. You just can take a 15 days trial, or you can just buy the monthly subscription for CloudxLab. All right, but here I'm not going to advertise what CloudxLab is. Okay, so at CloudxLab we are going to log in my home directory. This is no dependency on CloudxLab softwares. It is open and free for all, so you can just use it with any Python environment you want to use it with. Okay, you can use Python. You will have to use Python 3. All right, so this is the command to clone this repository. I'm going to go to my lab. Once you click on Jupyter, you will see something like this. Okay, here when you click on new and click on terminal, the new terminal will open. New terminal will open, and that terminal will look like this. Okay, in this terminal we are going to copy paste the command git clone and then the URL. Okay, in this URL, this command essentially clones the repository in your home directory. Okay, so you can go to, just to check whether everything is there or not, you can go to this folder. Okay, and type the ls command to see the list of files. So here you can see that there is this backprop from scratch, but no worries. If you do not understand the Unix command, it's completely okay. The purpose here is not the Unix commands. So we go back here in this folder, and here you will notice in the home directory of Jupyter, you will notice a new directory with the name IITR Deep Learning SPLTF2. Okay, there you will see backprop from scratch. You click on this and it will open this notebook. All right, so once you have this notebook in front of you, you walk with me through the code and understand line by line every part of it by the way of this video. All right, so the first idea that we are going to discuss is how to write functions in Python. Function is nothing but a sequence of operations, and we give a name to these sequence of operations. For example, here, what we are doing is we're defining a function with the name sq, or you can say square. It's taking an argument x, and it's returning the value x multiplied by x. So this function, you can imagine it like a box which is taking x and giving out y, which is nothing but x multiplied by x itself, that is x square, right? So this is how you can visualize the function. The function takes input by the way of arguments, and it returns value by the way of return values. All right, now let's move ahead. Let's define a function called square, the one that we talked about just now. So it's taking x as argument and returning x multiplied by x. All right, let's just test it out with 4. So you can see that it has returned 4 multiplied by 4, that is 16. And when I call it with 10, it returns 100. 10 multiplied by 10. All right, so further, a function can also take multiple arguments, right? For example, we can define a function add, which takes a and b, meaning the two arguments, and it returns a plus b. Pretty simple, right? So you can think of it like a box which is having two inputs like a and b, and it's returning a plus b here. So this is how you can visualize a function. Let's try to define a function. Here we are defining the function add. Def is a keyword that we are going to use while defining the function. We basically use indentation to mark the body of the function. So here we are saying that add takes two arguments a and b. Colon marks the starting of the body, and then it returns a plus b. All right, so let's take a look at this. So we are able to see that add is returning 10 plus 20, that is 30. Similarly, we can also test this. Okay, those who are wondering how to run a command in Jupyter Notebook, we basically run shift enter and it gets executed. Okay, in case you have a phone, you can always say cell and run cells. Okay, so here we go, and let's just take a look at another execution of a and b. Another execution of add a and b, right? So here you can see that we are adding 10.5 with 120, and the result is 130.5, right? I hope everybody is clear about this. All right, so next idea that I want to discuss is how do we pass multiple arguments to a function? Right now, we defined two functions. One is square, which takes only one argument, and then second function add, which takes two arguments, right? Now let's define a function which can take any number of arguments. Okay, all you need to do is put an asterisk. Okay, just have one argument and put an asterisk in front of it. And what it does is, when you call this function, it will gather all the arguments into this array. Okay, array or tuple. I think it's tuple, but for now you can just think of it as array. That will be easier to think of, right? So let's take a look at what's going on here. So here we are saying that this is the total value, and we are iterating over this list of values, right? This list of values, which is essentially the arguments, and then we are adding each of the value into S, and it returns S. So when we call the sum function with 1, it returns 1, right? When we call sum with 2 plus 3, it returns 5. Now you can see that sum can be called with 1 argument, 2 arguments, or 3 arguments, right? This is called the variable arguments to a function. Okay, this is called the variable arguments to a function. Next idea that I want to discuss is that if we have a function with fixed number of arguments and we want to dynamically call this function, right? And we do not know how many arguments are there. Okay, so how do we call it from the variable, right? Imagine that we have a list or tuple or an array holding all the values that we need to pass to this function. How will we convert that, right? So we have an array containing the 3 values. How would we call this function with this? So we'll just put an asterisk, which means convert this array into arguments. Okay, convert this array into arguments. Now you can see that we have defined a function add. Ideally, this should be called with 3 arguments, right? But here we are just calling it with one argument, with one argument, which is an array, and we're just putting asterisk. This asterisk is converting it into a call whereby this array is getting converted into the function argument. You can see that? So this is how you can call a function with fixed number of arguments with dynamic array. All right, I hope this is clear. You try experimenting with this, you will get more and more ideas around it. Next idea that we want to discuss is passing a function as argument. We want to show you, or we want to learn how to pass a function as an argument to another function. Usually in most of the languages, when we define a function like this one, right, it's taking an argument. This argument can only be normal values, but in Python, it can be a function. Let's take a look. So first of all, we are defining a function called double it, right? Double it, we could also define it, triple it, and so on, right? So right now we are just defining a function double it, which takes any value and doubles it, right? We'll be using it very soon. Now, we are defining a function called apply transformation. Okay, this is our function. And what we want to do is, we want to take a function, another function as argument, and call every element of this array with this function. Or you can say that we want to call this function on every element of this array. So what are we going to do? It's pretty simple. Let's say we allot an array for the output. Then we go over every element of this array and call this function with every element of this array. And whatever is the result, we append that result to this variable, right? Now, once we have done that, then we return the array. Let's take a look if it's working well or not. So you can see that it is actually working well. When we called this with double it, along with an array, the array value has been doubled. 1 became 2, 2 became 4, and 3 became 6, right? So you can see that this applied transformation has called this function with this argument first, then this argument first, then this, right? So applied transformation is calling this function on first, second, and third values from this array, right? Which means that this function can be used to call any other function on every element of another array. Like for example, here we're calling square on every element of this array, right? You can see 1, 4, 9. This way, we can call any function on any data. So this function is very generic, which can accept another function as argument. So this is basically how we pass a function as an argument to another function. All right, so next idea that we want to discuss is differentiation, or sometimes referred to as derivatives. Okay, so the differentiation is nothing but rate of change. The process of differentiation is basically about finding the rate of change of something with respect to something else. For example, the rate of change of distance is called velocity, or you can say speed. Rate of change of distance is called velocity or speed, right? And basically the rate of change of distance is with respect to time here, right? With respect to time. As the distance is changing with respect to time, that's called the velocity, right? Rate of change of velocity is called acceleration. And again, here rate of change is always with respect to something, and here it is time. If you plot rate of change of y with respect to x for a straight line, say for example here, how is y changing with x, right? It's constantly changing. Therefore, the change is constant, right? Change is constant from the beginning till the end, right? Similarly, if your y is changing in non-linear fashion, for example, if you have a parabola, in parabola, y changes with x non-linearly, right? In that case, when you differentiate that that function of parabola, you will get straight line because the slope or the derivative will be increasing consistently. Never mind if you did not understand the last point, it'll become very clear as we go ahead. All right, let's just stick to the basic definition, and that's what is going to be of use. So dy by dx, that's how we define the differentiation or derivative. We basically finding the rate of change of y with respect to x. All right, so it's pretty straightforward. How do you calculate it? Change x a little bit by little tiny delta amount, observe the change in y, and divide the change in y by change in x, right? It's pretty simple. So imagine that your y is changing with x in this curve, right? So when x was this, y was this, when x was this, y was this, right? This way, y is basically a function of x, and how would we compute the rate of change of y with respect to x at any point? Imagine that we want to find out the rate of change of y with respect to x at this point, right? So what we'll do is we'll increase the x a little bit, and with respect to this, whatever is the change in y, so the value of y at this x is this much, right? This much. And the value of y at this point, is how much? This much, right? So the rate of change of y with respect to x at this point is delta y divided by delta x, right? And if you look at it carefully, it's essentially the slope of this line. That's how we define the slope. Slope of a line is the change in y with respect to x, right? The vertical line divided by horizontal line, that is called the slope. So this is basically the main definition of differentiation and derivative, and we are going to stick to that. Also notice that this slope or this line is essentially a tangent to this curve because it's just touching it. Okay, so this is essentially the tangent to this curve. All right, so there are many properties to this tangent that we are going to talk about very soon, which will be used in our further understanding of gradient descent as well as the backpropagation. All right, so this is the basic definition of the differentiation. Using this definition, you can calculate anything. You can calculate the derivative of anything. For example, if you want to calculate derivative of x square, y equals x square, what you can do is just increase x a little bit, observe the change in y, and then subtract the 2, divide by the delta x, right? And you will find that very simply, okay? Now, using that, you can derive lots of formulas, lots of expressions, and you can utilize those expressions in your algebraic calculations. Okay, so this is basically the main definition of differentiation. Even if you studied long back, I hope this served as a recap for you. And if you're studying for the first time, trust me, if you just stick with the first principle or the fundamental principle of differentiation, you can solve anything. Okay, I'm going to show you that. Now, instead of focusing on algebraic differentiation, as in doing it x square and x cube and so on, we're going to focus on numeric differentiation. What does it mean by numeric differentiation? Numeric differentiation is about differentiating at certain point in the overall behavior. Let's take a look. Imagine that we have a function. Imagine we have a function square which takes x, returns x square. Now, how would we differentiate this function? Yes, sounds very awkward. You may not have studied earlier what exactly is differentiation. So let's try to see what it means by differentiating a function. Okay, so what we do is we stick to the first principle. All right, we increase x a little bit, observe the change in the returned value, and divide that change by the change in x, right? Let's take a look. So let's write a function called diff, which takes two arguments. One, the function that we want to differentiate, and the value of x. So you can think of it like this machinery, this box, we need to observe the differentiation of this, which is the change in output with respect to the input. We want to observe that. And so what we're doing is we're writing a function which takes this function as argument and differentiates it at x, right? So this is a function, this is a numeric value. So what we do is, first of all, we define delta. It is really tiny value, really tiny. You can increase one more zero here, it will not make much of a difference, okay? So this is really, really tiny value, okay? So this delta is really, really tiny value. So what are we going to do is, we are going to first calculate the value of y, which is output of this function at x. Then we are increasing x with tiny amount. We are increasing x by tiny amount, right? And remember that in differentiation, the way we calculate delta x is, this delta x has to be really tiny, okay? So we increased x with tiny amount, and then we found out the returned value on this value, which is x plus delta x, right? So the rate of change in output is y1 minus y, right? And rate of change of input is x1 minus x, correct? So this should give us the numeric differentiation of this function. Let's test it out. So diff of a square at x equals to 2 is coming out to be 4, right? Those who are coming from algebraic background or analytical differentiation background, they will quickly recall that the differentiation of x square is 2x, right? And since we computed at x equals 2, therefore 2x is how much? 4. So our calculation was right. Don't worry in case you don't know or don't remember what was analytical differentiation. This won't be used in this particular tutorial. Okay, in this particular tutorial, it won't be used because this one, in this tutorial, the only thing that is going to be used is mostly the numeric differentiation. All right, but it's good to know that the differentiation of x squared is 2x. All right, now you can see that this one is giving the correct result. Similarly, let's try out with cube. Okay, so the way we define a function cube is basically it takes a single argument and returns the cube of this value. How do we calculate cube? We multiply a number by itself twice, right? So we get cube. So x multiplied by x multiplied by x. So we multiply x with itself twice. And it seems to work fine, right? So cube of 10 is supposed to be 1000. Now let's test out whether the differentiation of cube is 12 or not. The differentiation of cube is working or not. Okay, so when we run it, we get 12, right? we get 12. So essentially, the rate of change of output with respect to input at x equals to 2 is 12. Okay, what it means is y is changing 12 times than the x. The slope is really high. Slope is really high at that point of time. Okay, so this is what it means by differentiation. Now let's see if it is really right. So what we did was we recalled how we calculated differentiation, right? So the differentiation of x to the power 3 is 3x square, right? It is 3x square. So you can calculate the same thing by using a simple mechanism to do the maths, the algebraic one. But you also prove that the differentiation of x to the power 3 is 3x square. You can prove it using simple algebraic calculation, just like what we did just now, right? You can increase x, observe the change in y, and then divide by delta x, and basically remove the tiny fractions because delta x is going to be really tiny. Okay, so with that kind of mechanism, you can calculate this. Even if you do not know algebraic differentiation, do not panic at this point because that's not going to be used. I'm using this algebraic differentiation just to prove that our function is working. Okay, our function is working. That's the only reason I am trying to put forth the formula. But do not worry in case you don't remember this formula or do not know this formula, because this is not going to be used. What's going to be used is this function. Okay, so you can see that this one is also giving 12 and what we found is also 12. So our function of differentiation seems to be working. So just now we learned how to differentiate a function with single argument. All right, so far we only differentiated the function with a single argument. What if there is a function which is taking multiple arguments as input? Or you can say that if there's a function which is taking multiple inputs, how do you differentiate it, right? So the idea is simple. The idea of partial derivatives is simple, that we always differentiate the output with respect to a single input, right? Or you can say that we differentiate the output of a function with respect to the single input at a time, considering the other inputs to be fixed. Okay, so here is a function which is taking, let's say, two arguments. Okay, it's taking two arguments, x1 and x2, and we want to differentiate this function. This function is returning 5 times of x1 and x2 square. Now we want to basically differentiate this function. Now if we differentiate this function with respect to x1, right, what will happen is we will think of this as non-changing. X2 is not changing, therefore this is constant. Okay, and hence this will be eliminated in the difference, right? So differentiating a function with respect to one of the inputs is essentially considering the other inputs as fixed. Similarly, when we are differentiating this function with respect to x2, what we're going to do is we are going to consider this part as constant. All right, let's, instead of thinking of algebraic, we will think of numeric. All right, so let's say x1 is 10 and x2 is 20. So what would be the output and what will be the rate of change of output with respect to the inputs? Okay, so we say that delta x is this much. Delta x for both the cases, x1 and x2, it's same. It's really tiny value. Okay, now delta y is essentially the value of a function the value of the function on x1 plus delta, x1 plus delta and x2, right? Minus the value of the function at x1 and x2, meaning we change x1 a tiny bit, observe the rate of change of the function's output. Okay, that's delta y. Okay, so rate of change of this function with respect to x1 is delta y divided by delta x, right? That's how we defined the main differentiation or main derivative. Okay, so df by dx1 is how much? Approximately 5. Let's just take a look. See, it is 5. Now, if you want to differentiate the same function with respect to x2, what we're going to do is we're going to increase x2 a little bit and calculate the function's value as x1 and x2 plus delta, right? And subtract the value with the value of the function on x1 and x2, right? Notice that this time we are only changing the second argument. Earlier, we changed the first argument. Right now, we are changing second argument, keeping the first argument as such. So, delta y is this much. Okay? Delta y is basically the difference in the value of the output when we changed x2 here. Okay? So, the rate of change of function or rate of change of output of the function with respect to x2 is delta y divided by delta x, which is df by dx2. Okay, so it seems to be it is like approximately 40. Okay, so if you are differentiating with respect to x2, right, it's going to be 2x2, because if you remember the algebraic differentiation, you can quickly cross check. Okay, though if you do not remember algebraic differentiation, never mind, it's not going to be of much use. Here we are just using it to verify if our results are correct. Okay, so it seems to be correct, and it is correct actually, I know for sure. And right now we are just taking the most simple code so that we all can understand. There can be further optimizations in the differentiation. Okay, now this was how we differentiated this function manually. What if we have to differentiate any function? We have to differentiate any function with variable number of arguments. There could be a function which takes 100 arguments. There could be a function which takes only 5 arguments, and we want to differentiate that. So let me show you how I would write that kind of a function. Okay? Here, what we are doing is we're defining a function called diffp. It's on the same lines as what we did earlier. This function we are designing such that we can differentiate any function. This function should take the function itself, right? It should also take the number of the argument with which we want to differentiate, and all of the arguments. Earlier it was only x1, x2, but there could be x1, x2, x3, x4, x5, and so on. Therefore, what we are doing is we are defining a differentiation function which takes another function that needs to be differentiated, and it takes all the arguments with which this function need to be called, and this extra index. What does this index represent? This index represents with which input argument we want to differentiate. Okay, for x1 it's going to be 0, for this x1 it's going to be 0, for x2 it's going to be 1. So this starts with 0. So 0th value of this argument. Okay, now what we're doing is we're first calling the underlying function with these arguments as such, right? This is how we defined it earlier in the discussion, that if you have an array of values, you can call the function with that array using asterisk. right? So this function could have like 10 arguments, 20 arguments, 1 arguments, 2 arguments, and so on, right? Now, so we called the function on those arguments as such, meaning we calculated the value of y at all of these arguments, x1, x2, x3, x4, and so on, right? Now, what we do is we increase the ith or indexed argument, okay? We increase that x with which we want to differentiate by tiny bit of delta, okay? That's what is going on. So we converted first this argument into a list, okay? And then we increased ith argument with delta. Why did we convert this? Because usually it is a tuple, and since we are changing the value, we are converting into list because tuples cannot be changed, right? So we are increasing that ith x. It could be x1, x2, x3, x4, x0, whatever. So we are increasing that particular value by a tiny amount. Notice that all other values of arguments are as is. Only one of them has been changed. Which one? The index of which is supplied as the second argument to diff_p, right? Now, on this new value, new array, or you could say the same array, but one thing has been changed with delta. We're calling it, right? So this is the new y, this is the old y, and the difference between previous x and new x is delta. So how much did the input change? By delta, how much did the output change? Y1 minus y. All right. So this is essentially formalization of this. Okay. This is essentially generalization of the approach we took earlier, right? Because there could be a function which is taking like 9 arguments, 8 arguments, 100 arguments, and so on, right? Now here we call this function. We define this function. Now moving ahead, let's take a look at this. Imagine we have a function called line underscore y, which is taking 3 arguments, m, c, and x. Now, if some function is taking 3 arguments as input, we can differentiate this function with respect to 3 values, m, c, and x, right? So here, let's take a look. So we define the function, we want to differentiate it with respect to m, for example. So how will we call? We will call our function diff_p. We'll pass this function as first argument, and whatever values of m, c, and x are there, that's the last argument we are passing. So say m is 1, c is 2, and x is 3. So these are the values of m, c, and x. So what we are saying is differentiate this function where m is 1, c is 2, and x is 3. At that point of time, differentiate it with respect to 0th argument, that is this one. Okay, so we are differentiating this line y, line underscore y, this function with respect to m. Okay, so the result is 3. Similarly, we can differentiate this function with respect to c, right? Second argument here. So we pass here, instead of 0, we are passing 1, right? So what's going to do is, what this function is going to do, diff_p is going to do, first it will call this function on 1, 2, and 3, right? And then it's going to change this one a little bit, okay? Because we have said 1, this is 0, this is 1, this is 2. So it's going to change this a little bit, observe the change in output of the line y, and then divide by delta, right? That's what is going on in this. So this one is 1. Similarly, we can specify 2. 2 means differentiate it with respect to x. Okay, in that case, the result is again 1. Perfect. So this is called the partial derivative. This is called the partial derivative. Okay, I hope this idea of partial derivatives is clear to you. Okay, never mind this now. This import, we'll talk about it soon. All right. So this is essentially how partial derivatives work. Next very important idea is the chain rule. Chain rule is a very interesting rule. Okay, though it might look pretty obvious, but we are going to see that this is very much applied, and it's very interesting when it comes to neural networks. All right, so imagine that we have a chain of functions. So let's say input x is given to square, right? So it'll become x square, and then whatever is the result is being cubed. Okay, is being cubed, and the result is basically a cube of t, right? And the result will be x squared to the power 3. Okay, now the important part is this, that here we can differentiate y with respect to t, correct? Y with respect to t, and t with respect to x, and also y with respect to x, correct? We can basically think of it like this is a big box, right? This is a big box, and this big box is something that can also be differentiated, right? Do not get confused with this x. It's essentially t here. Okay, so this is basically t, right? This is because t is the input and y is the output. Y equals x t to the power 3. Okay, so don't get confused with that terminology. Just that this should have been t. Just for the sake of generalization, we have defined the function always in terms of x, in terms of argument being x. All right, so the chain rule is given this differentiation, what will be the overall differentiation? Or you can say, given this derivative, what will be the derivative of overall? Or in other words, if we are given the dt by dx, dy by dt, what will be the dy by dx, right? So answer is very simple. Dy by dx is equal to dy by dt multiplied by dt by dx. All right, let me show you what it means. Imagine that we have two functions. Square of x returns x squared, cube of t returns t cube. Okay, and this chain can also be another function, right? You can imagine there is a box in which these two boxes are contained. That is this, right? It's taking x, it's returning y. First it computes the square, then it computes the cube. Notice that this cube is being called on t, not on x, correct? Because the output of the previous step is being fed to it. Okay, so this function is what we are interested in differentiating. What will be the derivative of this function? Okay, let's take a look. Diff p equals diff p is being called with sqcb, and we are basically passing an argument x equals to true to, because whatever argument we pass from third argument onwards, they'll be passed to this function as is, right? So we are differentiating this function with respect to 0th argument, which is x. So we're differentiating it with respect to x. Let's take a look at the result. So it seems that it is 192. Okay, this is 192. Now, let's understand if the chain rule that we're going to talk about also gives the same result. Please notice that here we really did not need to know what is inside this black box. Okay, so we are differentiating or finding the derivative of a black box using this simple technique that we discussed earlier. Okay, so now the chain rule says that if there is a function f1, okay, so the value of y is a function of t, okay, and the value of t is a function of x, right? So y equals f1t and t equals f2x, okay? In that case, The answer is simple. Rate of change of y with respect to x equals to rate of change of y with respect to t multiplied by rate of change of t with respect to x. Okay, this is basically what we call the chain rule. Okay, let's take a look if it also gives 192. So first of all, we differentiated the square function. Okay, we differentiated the square function, right? That means we are calculating dt by dx. Okay, we are calculating dt by dx, right? So this is basically the differentiation of the x square, right? We can also write it like dt by dx, correct? dt by dx. Now, here we are further going ahead, calculating the value of t on x, which is x square, right? Now, at this value of t, we are differentiating cube, okay? So we are basically calculating the value of rate of change of y with respect to this, correct? So dy by dt, okay, is this much differentiation of cube, dy by dx is differentiation of square, right? So the result is this multiplied by this, okay? Let me just calculate from the beginning. All right, the answer is simple. It's 192. So this is how we calculate the partial derivative. So we can do two things, and we'll show you that we can actually use both the techniques. Okay, this technique whereby we basically create another function, bundle both the functions together in a sequence, and then differentiate overall function. This technique is way more easier. Okay, this technique whereby we differentiate each individual boxes, differentiate this, multiply the two together. Okay, when we do that, that one is little more, requires two steps, but this one could be efficient. Okay, you will see that first we will do the back propagation using the first technique, and then we will use the second technique. Okay, so essentially either we let the system do the differentiation or we can ourselves multiply. All right, so this is basically what we call the chain rule. Chain rule says that dy by dx equals dy by dt multiplied by dt by dx, right? This one. This is the chain rule. All right, so let's take a bit of digression in order to understand what exactly is gradient descent. We learned that we feed the data having instances with features along with the expected output to the algorithm which generates the model. Then this generated model can predict the output from the live data or the input for which we do not know the labels. But what's there in the algorithm that generates the model? And what does a model mean? Let's try to answer these questions. Let us take a really simple example of predicting the salary based on the number of years of experience. Say after first year your salary was 2000 and after the second year your salary became 4000 and the third year 6000. What will be your salary in the fourth year? That's right, it is 8000. Let us convert this problem into instances, features, and labels, and see how to make the computers solve this problem. In our case, there is one feature, years of experience. In real life, there could be multiple features, such as the area of expertise, the location, etc. And there is one target or label, salary. We would want to train a model such that the model can predict the salary for the fourth year. Here, the model has predicted the salary for 4 years of experience as 8000. Now let us understand what goes into training it. A simple way to solve it is to just plot it on a chart.
The horizontal axis being years of experience and the vertical axis being the salary. And once we are done with plotting, we can figure out the salary for the fourth year, which turns out to be 8,000. Here, we were lucky to have perfect data with which we could draw a straight line. What if our data was more like real world data where we don't always get a perfect straight line? Say if the salaries for the 3 years were 2010, 3980, 6020, can we draw a straight line that passes through all the points? No, we can't. So, what do we do in this case? How do we figure out the salary for the fourth year? The first strategy is to come up with a straight line that is closest to all the points. This approach is known as linear regression. Though there are various ways to do prediction, which we'll talk about later, for now, what could be the definition of the best fitting line? The best fitting line, or the line of best fit, is a line which is closest to all the points, meaning it has minimum error. So, we could find the average of total deviations, and we can calculate the total deviation either by summing up the absolute differences or the squares of differences, and find a line which has the minimum error. Let us visualize the error. In this diagram, line 1 has the minimum error, and hence it is the best line as compared to line 2 and line 3. So our machine learning algorithm needs to come up with such a line which has the minimum error. Here, each line is basically a model. The model or line that algorithm comes up with will be used for predictions. We could create a simple algorithm that iterates over all possible lines and keeps the best line so far. Such an algorithm will basically try lines with all possible slopes and distances from the center. What do you think is the challenge with this approach? It will take a huge amount of time to come up with the best model even in such a simple case. Why not try to go to the side where the error is reducing? One such approach is gradient descent. Let's understand this approach. Say we start with a random line with some slope and intercept. And then we try increasing the slope a little bit and observe the change in error due to the change in the slope. Here we have three instances 2010, 3980, and 6020. To compute the change in the error, we will have to check with all the instances. If the error is decreasing, we continue to increase the slope at a faster pace. The question is, how much should we change the slope to get the next line after each probe? In simple words, the increase in the slope should be proportional to the rate of decrease in error. The more the change in error, the more we should change the slope. So we can say that the increase in slope is equal to some constant multiplied by rate of decrease in error. Please note that this decrease in error is with respect to the change in slope. So now we can say that the new slope is equal to old slope plus the change. And the change is learning rate, which is some constant number, multiplied by the rate of decrease in error. If the error is increasing with increasing slope, we decrease the slope as in the diagram. This method is called gradient descent. Gradient means the rate of change and descent means going down. We go to the side where the gradient of error is going down. Since a line is defined by slope and its distance from the center called intercept, we do same tweaking for the intercept too. Since the gradient descent is the core algorithm in machine learning and deep learning, we would spend some more time on this. Say we are trying to find a line that fits our data points. We start with a random line. Here, the line is our model because using this line, we will be doing the prediction of salaries as we did earlier. We then slightly increase the slope and calculate the change in error. Also notice that to compute the change in error, we will have to consult all the training instances. If the error decreased due to increasing the slope, we continue to increase the slope in a greater amount proportional to the rate of change. Otherwise, if the error has increased, we go in the opposite direction that decreases the slope in the proportion of the rate of change. Larger the change in error per change in the slope, larger the tweaking we do in the slope. If the error did not change due to change in slope, we stop because we have probably found a line that is the best fit. Afterwards, we go back to tweaking the slope again. It is called the next epoch or the next iteration. We continue doing it until we find the error is no longer changing due to tweaking. The model is the line which has two parameters, slope and the intercept. Also note that the way we tweak the slope, we would be tweaking the intercept too. Let us take one more example to understand the gradient descent. Say you have checked into a new hotel in winter and you have to take bath and you do not know which side you should be rotating the knob to give cold and hot water. What would you do in order to get the best temperature of the water for yourself? Think for a moment. One approach could be that we start with the knob at extreme left and try all orientations. But that would take too much time as well as it would waste lots of water. Could you think of a better approach? Please take a moment to think. Alright, so this is what we would do if we follow the gradient descent algorithm. We will start somewhere in the middle or any other random position of the knob. Check the water if it is of the right temperature. If it is, then there is no point in tweaking further. You have found a comfortable temperature and you can take bath. If the temperature of the water is not comfortable to you, either because it's too cold or too hot, you would like to tweak the position of the knob. Now, you slightly rotate the knob to the right and check if the temperature is going towards your comfortable side. Then, rotate in the same direction by a larger amount. And afterwards, we continue the same process again. If in the previous step, rotating slightly to the right was taking the temperature of the water to uncomfortable side, either too hot or too cold, we would twist the knob to the left by a large amount. Once we have found the comfortable position, we can mark the angle, and this is what we call our model. This particular model has only one weight, that is an angle. The algorithm that we have used was gradient descent. In machine learning, we can make the computer use the gradient descent to tweak the model such that the model starts performing well first on the training set and then on the test set. Also notice that once you have trained the model, running it is generally very fast. Only the training takes time. Now let us extend the same example to two knobs. What if we have two knobs, maybe one for cold water and other for hot water? But you do not know which one is which. Now in this case, you will have to tweak both the knobs simultaneously in order to get the right flow and comfortable temperature. So in this model, how many weights do we have? Two, right? At the end of training or tweaking, we would get the two positions of the knobs. In this model, we would be able to get two outputs, the right water flow and a good temperature. But we have more weights to train, and hence the training will take more time. we can represent the same using this diagram. What if we had more parameters such as climate, person's details, and the input temperature? In that case, we would require a lot more weights or knobs, and the model will be very complex.
Now that you have understood what exactly is gradient descent, let's try to implement gradient descent in our own way. Alright, so let's start with a very simple mechanism. We are assuming that now you understand that essentially what we are trying to do is given a function, right? Given an error function, we are trying to reach here. We do not know what is this point of let's say minimum of y. Okay, we could be here, we could be here. So we're going to calculate this value here. We're going to also calculate the slope, and in the proportion of how big is the slope, we are going to either go left or right. If the slope is negative, we are going to increase x. Okay, if the slope is positive, this is positive, we are going to decrease x. All right, that's what we are going to do. And in case the slope is bigger, we're going to jump with bigger amount. If the slope is smaller, we're going to stop here. Okay, because here the slope is 0. Because wherever the slope is 0, that means this line has got the minima there. Okay, so if we are here, we're going to jump this much, and next time we're going to jump by a tiny amount, meaning the slope is going to be smaller here. I mean, it's smaller in terms of magnitude. Okay, as compared to this one is more steep, this one is less. Therefore, we're going to jump by a little bit, then we're going to jump a little less, then we're going to jump a little less, and when we reach here, we will stop here. Okay, that's what we are going to do. At this point of time, when the slope becomes 0, we are not going to move x at all, right? So how much are we going to change x? In proportion of rate of change of y with respect to rate of change of x, right? That's what, if this slope is bigger, we jump by bigger amount. If the slope is smaller here, we'll jump by smaller. Also, if y is increasing, right? Y is increasing, let's say here, on increasing x, the y is increasing. So we have to decrease x. Therefore, we put a minus sign here. Okay. Also, please notice that a differentiation could be negative or positive. This one has negative slope. This one has positive slope. In this case, x needs to be decreased because there is a minus sign. In this case, x needs to be increased because there is a minus sign, and this one is negative, and so on, right? Therefore, we basically put a constant here called eta, or we call it learning rate, sorry. So how much are we going to jump is this amount, okay, which is proportional to rate of change of y with respect to x. All right, we put a sign here, yes, like this, correct? So next value of x is going to be x1 minus eta of delta y by delta x, correct? Now you can right, you can remember this way, that if this is negative, what's going to happen to x? X is going to increase. This is previous value, this is next value. If this is negative, this will become positive, and so on. And if this value is positive, then we are going to increase x. So if we are here, which means this is negative, we are going to increase x. If we are here, the slope is positive, therefore we are going to decrease x. All right. If this amount, the total amount, is big, as in it's really high, or this is really magnitude where this is high, we're going to jump by a bigger amount. And then when this is smaller, when we are going to jump smaller. So you can see that. This is called learning rate. Okay. This is capped because what if this amount comes to be really high? Okay. If this comes to be really high, we could jump like this. Okay. Instead of coming here, we could jump really far away. And now again, it is further, and therefore it'll go back and go back. So this will never reach here. Instead, it'll keep on going out. Therefore, we get a handle to control it. In case we observe that we are not converging, that means this value is really high. So we'll decrease this value. Okay. So basically, this is to control the amount of change you want to bring in. Okay. We know that it is proportional, but how much? Okay, how much should it be the rate? Should it be the fraction of this one? All right, so this is essentially what is gradient descent. All right, let's implement it. Enough of theory, so let's try to implement it. Okay, now when we have a function and we want to find out at what point this function would attain a minima or maxima, we try to use gradient descent. Gradient descent is mainly for minima, not maxima. Okay, so all right, now let's move ahead. First of all, what we're going to do is we're going to generate data. Okay, so we're going to generate a set of data. So first of all, we generated X, which is nothing but 100 numbers randomly generated. Okay, this is going to be between 0 to 1, so we multiply with 2, so it becomes between 0 to 2. All right, so we get X as an array of 100 numbers which are between 0 to 2. Okay, now we calculate Y. Please note that we are trying to generate data which is roughly around a linear line, right? So we say that mx plus c. So this is a constant plus 3x, right? So essentially this is a line 3x plus 4, okay? And we are adding a noise here. You see that? We're just generating some random number, multiplying it by 0.3 and then adding to it, okay? Also note that this is an array. This is an array. Okay, so basically what we are trying to do is we are basically generating 100 values of y corresponding to 100 values of x based on this. Okay, let's take a look at first 3 values of y. Okay, let me just run it. Don't get confused with the numpy and all. So it's pretty simple. We are just using it to generate an array. Okay, we could have used simply Python. We wouldn't really need to know even numpy. Okay, just that numpy allows us to manipulate arrays, list of values very easy. Like for example here, 3x means the whole array is multiplied by 3. And plus 4 means the whole array which was multiplied by 3, we're adding 4 to each value after multiplying by 3. And then here we have got 100 random numbers. We are adding correspondingly each random number with the value. Okay, so essentially doing the iterative work has been made so easy that this code looks really neat, right? Otherwise we'll have for loop going over and over and so on. All right, let's take a look at first 3 values of y. Okay, let me just run it from the beginning. Yes, so you can see that first 3 values of y is this much. Let's take a look at first 3 values of x, right? So based on, if we just go with this, based on first 3 values of x, how much is y? We just calculated 3x plus 4. It is similar, you can see that it is similar, right? It is similar to y, right? Just that we added some more noise to generate y, this part, this fraction, correct? So now that we are clear about what we did just now, let's just take a look at the data also. So we are using a library called matplotlib, okay? This is essentially for visualizing it, this is essentially for visualizing the data. Let me just try running it again. And okay, yes, now it has shown. I just needed to rerun it. Now you can see that this is x going from 0 to 2. This is y going from 0 to 0 to, I think, 10 plus. Okay, and this is like little random, but you can see clearly that there will be a line that is fitting it. And this data is like more like real life because it has a lot of noise. But it's very clear that there will be some line which is fitting very well. Okay, so when we draw a line, we are saying that there will be some error, right? As we learned earlier, there will be some amount of error. How much is that error? Let's calculate. Given some random line, a line is defined by a slope m and the intercept c. And these data points, what exactly is the error? First, we calculate the value of y on each of these data points, right? Each of these x, we calculated what is the predicted value by our model. What is our model? Mx plus c. So basically we calculated the y predicted by this line, which is very much straight line, okay? And for whatever value of m and c, it calculated the predicted value of y on every value of x, correct? Then we subtracted the predicted value from actual, right? And then we squared it and then summed it. Summed it for all data points, all 100 data points. So that's the overall error. That's the overall squared error. Okay, this is overall squared error. So we can just test it out. The error of a line which has 3s slope, 4s intercept, and this with 3 values of x and 3 values of y, how much is the error? 200. Okay, 200. Let me just try running everything. Now, if we have like, if we just try to put it like 3 and 4, the error we get is this much. Okay, notice that if we try to run it, if we try to increase this a little bit, you can see that the error has increased. Therefore, this seems to be the perfect line, right? Also, if we say this, yes, so this seems to be a better line than this one, okay, because this slope is giving lesser error, right? And we could also try this. This is increased, right? Okay, this is increased, right? So instead of reiterating this way and trying to figure out what is that value of m and c for which the error is minimum, we are going to write a function called the gradient descent. Okay, so here we are trying to do that. We are trying to locate those values of m and c for which the error is minimum. Okay, we could keep on doing hit and trial of m and c, the slope and the intercept of that line, but we will never reach. One way could have been that we iterate through all possible values of m and c and then see what is the result. Now, if there are 1 million values for m and 1 million values for c, there are going to be total 10 to the power 12 permutations, which is like really, really crazy. And it is not really possible to try all of those. Okay, so this function, we need to figure out those values of m and c for which the error is minimum. Let's try to do it programmatically and try to follow this approach. Okay, try to find out the values of this line m and c. We try to find out those values of m and c for which the error is 0. Notice that here it's x and y, but in reality, what we are going to do is on x-axis it's going to be m, on y-axis it's going to be error, because we want to find out the value of m for which, this value of m for which the error is minimum, right? For which the error is minimum, correct? So it's pretty simple. First of all, what we're going to do is we're going to take a random line. We're going to pick the value of m and c randomly, right? Then we're going to iterate for 100 times. So we're going to first find the rate of change of error with respect to m. Okay, we're going to find the rate of change of error with respect to n. Correct? And how do we do that? We call our function, the one that we defined earlier, diffp, give it the error function, right? Give it all these 4 arguments, m, because it takes 4 arguments, m, c, x, y, right? And here we're trying to find the error, the change in error with respect to m. Therefore, we're going to pass 0 because this index of this argument of m is 0. This is 1, this is 2, this is 3, correct? Now, similarly, we are trying to find out intercept also. So we find out how is error changing with respect to the intercept. So diffp, and we are passing the error, and we are passing all the 4 arguments, and we are basically putting 1 here. All right. So we first of all chose m and c randomly. These are 2 constants because this is the data point that is given to us. And this is something that we are trying to figure out. Okay. As opposed to the nomenclature that we have studied so far, in which x and y is something that change, m and c is constant. No. Here, our agenda is to find that line which fits this data set to us. This is the observation from the industry. Okay, so the new m is equal to the older m minus learning rate multiplied by dE by dm, which is essentially this, right? So we initially chose randomly, m we chose randomly. Now the new m is going to be m minus learning rate multiplied by dE underscore dm. Similarly, c is going to be how much? C minus learning rate multiplied by dE by dc. Right? Thumb rule is whatever quantity you are trying to tweak, that remains here. Okay? And whatever quantity you want to find out at 0, like error in this case, we want to reach to the 0, that is the one that remains here. Okay, so we find out how is error changing with m and keep on tweaking m. We find out how is error changing with c, we keep on changing c. Right? Now, let's try to call this gradient fit with x and y. So it's going to do this whole process 100 times. Okay? Now it has done the job. Okay, it has done the job. Let's take a look at value of m and c. It should be something like 3 and 4. Yes, almost. You can see that. Let's take a look at the line. This is our perfect line. You can see that. So our gradient descent essentially kept on tweaking this line until it reached here. And it reached in 100 iterations. In order to understand how much time did it take, really, let's just try doing it again. Okay. So this is the line. Also, in these cases, what we generally do is we also calculate the error and print that error on certain data set. So let's say 15% of the record, we keep it aside, and at every iteration, we print the error. How is the error going? We will be able to figure out the overall error. Okay, so let me just try to call error here. Okay, in the beginning, correct? In the beginning, on the ith iteration. So we'll say print here. This is my ith iteration. Okay. And we are saying error here, error How much is the error? Let's just put these 4 values. Okay, just to show you that it converges really fast. Okay, and let's try to do this. So initially, you can see, initially the error is very high and then it drops pretty fast. But after it has reached, the almost like minima here, it starts going slowly down. So ideally, we should just stop somewhere. If we don't have enough processing power, we should generally just stop here or probably maybe here, right? On the 42th iteration, okay? Because afterwards, if we had 100, let's say if we had 100 iterations here, after say 40, it doesn't really go well, right? Let me just show you. It is of no use. You can see after a point of time, it's just 10.9, just 10.99, right? Therefore, it is just better to stop somewhere, maybe here or something like that. Correct? So because it is essentially almost flat. Okay. One more thing I want to show you is imagine that learning rate was very high. So it won't converge. Instead, it will keep on increasing. You see that? So initially the error was this much, then suddenly it went further high, and it kind of just kept on increasing. Okay, this is the maximum error we could attain. So for some value of MNC, it just did not converge at all. So for some value of this learning rate, it did not converge. Similarly, we could, and remember that all of this is coded by us just now. Okay, so you can see that even the lower value of learning rate is okay. All right, now 0.01, let's just see how it goes. All right, it actually reaches 11 pretty fast. So you can see from here to 12 or 11, it goes very fast, and then it basically kind of goes really slow. So we could have like other kind of things like early stopping. When our error is not dropping enough, like we keep a store of like previous error and compare it with the new error, and if that error is not dropping enough, we can just stop early instead of going into iteration. Okay, so the point that I'm trying to make here is that once you know what's going on, once you understand the psyche of gradient descent, if you code it by yourself or you try to go through this code line by line, you will be able to innovate and you will be able to solve really hard problems with gradient descent. All right. So I would strongly suggest that you try to code it by yourself. Okay. So that's the gradient descent, and then we try to plot it. Now, since we did not iterate much, let's say the iteration was say 5. Okay, let's just take a look at the new line that we have. Okay, this new line is not really well fitting because we stopped too early. But still, it was able to reach somewhere at a decent place, correct? If the iteration was like 1, the line would have been like really bad, correct? Line would have been really bad. Also, inside this loop, you could plot your own graph at every MCA, right? That you can try to do that. Like here, the way we are doing it, you could also do pi subplot and do that. Okay, try doing that, and you'll get lots of beautiful lines and at various iterations. So that'll give you an idea how it is converging. Okay, so try experimenting with it. This is extremely important. So right now what we did was our own we learned to code our own gradient descent. All right. All right, so the next topic that we would like to discuss is backpropagation. Now, let's take a bit of digression to understand the backpropagation, and then we'll come back.
Now let's try to understand neural networks. The algorithms fashioned based on the working of an animal brain. In the recent past, the artificial neural networks are doing an incredible job in predicting. This is a simple representation of how neurons are connected to each other. Notice that all inputs are connected to all the neurons, and each neuron is also connected to other neurons. Here, the input layer is represented in red, and the output layer is represented in blue. A simple neural network has only one layer of neurons between the input and the output, otherwise known as the hidden layer. And a deep neural network has many hidden layers. Let's go back to the earlier example of knobs controlling the temperature of the water. But here, instead of just two knobs, we have five knobs linked to the five input features as shown. We need to turn the five knobs in any direction to give us the right flow and temperature of the water. What will be the right positions of the knobs to get the right temperature? If we rotate individual knobs, we can come to a combination of knob positions that can give us the right temperature. We can further improve the result if we add another layer of knobs such that the output of the first layer of knobs goes as the input to the second layer. We have another set of five knobs to fine tune the output of the first layer of knobs. Predictions could be improved further if we add a third layer of knobs. This can be a generalized analogy to a deep neural network with three hidden layers. We have seen that training a single neuron can be easily done using gradient descent, but how can we train a network that has two knobs or two neurons? Imagine the same scenario in the context of neural networks and think of these two knobs as neurons. Let's see a simplified version of neural network. We have the same two inputs, hot and cold, and our objective is to get the right temperature. Let me introduce a new concept here called backpropagation or backward propagation of errors. To be clear, the knob on the left we are going to call it as first, and the one on the right we are going to call it second. Let's start. The first step in the process is called initialization, where we assign random positions to both the knobs. Based on the position of the knobs, we calculate the temperature of water that is coming out from the first knob, the interim temperature, and also find out the temperature of water that is coming out. And then note the difference in the temperature with respect to the ideal temperature. This is called the forward pass. Now we start the back pass. In this step, we freeze the first knob and tweak the second knob a bit and observe the impact on the output. Did the temperature go to the right side or wrong side on rotating the knob slightly? If it was going in the right direction, we rotate the knob further, else we rotate the knob in opposite direction. This is basically gradient descent. In this step, we rotate the second knob once. We now freeze the position of the second knob and tweak the first knob. Essentially, what we are doing here is adjusting the first knob by learning from the difference in temperature. This is called backpropagation. We now have a revised position for the first knob as well, and we are closer to the ideal temperature. We now go to the next iteration or the next instance, and the process repeats starting from the forward pass step. Let's get a real perspective of artificial neuron. It is basically a software construct. Let's get into the structure of neuron in the context of artificial neural networks. We have already seen that we get an output from the neuron based on the input provided to the neuron. Apart from the input and the output, The two other components that you need to know are the weight and the bias. Imagine the weight and the bias to be two knobs that need to be tweaked. With respect to a neuron in a neural network, input is multiplied by the weight and the bias is added to get the output. Now, a common question people ask is, why do we need bias? Isn't weight sufficient to do the prediction? Can't we achieve all results by just having the weight without the bias? Let me take the same salary example with a little different data points. Imagine that you started your career with a salary of 1000, meaning at the experience of 0 years, your salary was 1000. And then after 1 year of experience, your salary was 1500. And after 2 years of experience, your salary became 2000. The question is, can we fit a straight line into this data that is going through the center? We have two parameters to define a line. One is how slanting is the line, that is the slope, and where it cuts the y-axis when x is 0. So, by varying two things, slope and the intercept, we can achieve the best fitting line. Similarly, in neuron, we have weights and the bias. Bias signifies that even when the input is 0, there could be some value. Now, let's extend this to a network with two inputs. We take into account both the inputs, their corresponding weights, and the bias. The output is a function of these weights and bias, as represented by the equation shown. In other words, you can say that the output is a weighted sum of inputs plus bias. The researchers further discovered that if we pass this output through a transformation called activation function, the final results are far better. Let me explain what it means by an activation function. The role of the activation function is to accept or reject the computed value from weights and bias. It is based on whether the value coming out of the neuron is either too low or too high. We can simply represent the neuron having the activation function inside it. An activation function is a mathematical function to convert huge value into something smaller and also very small values into something closer to 0. So idea is to convert the result into 0 or 1, just like converting an analog signal to a digital signal. To further visualize the activation function, imagine a function within the neuron which works like a switch, which turns a circuit on and off based on the magnitude of the value that is coming out of the neuron. Thus, the activation function makes the neuron behave like a switch or logic gate. If we combine a bunch of such neurons and connect to each other just like that of a series of circuits on an electronic circuit board, we can get a very complex network of neurons that can do amazing predictions. So, training a neural network is more like automatically coming up with a circuit using the data that could give desired results. But how would we train such network using historical data? This is done using backpropagation algorithm. Let's understand backpropagation algorithm again with an example. Let's take a dataset with work experience and salary of 4 different employees. We will try to train a neural network with this training data. Here, our input features are work experience and the label is salary. Here, we are taking a simple example of two neurons. We call the left one as the first and the right one as the second. In this case, we have two weights and two biases, meaning we need to tweak these 4 knobs. We want to come up with the positions of various knobs such that this neural network starts predicting salaries based on work experience. Also, to make the calculation simpler, we are not using activation functions in neurons. We go through the initialization phase where we assign random values to the weights and the biases. In this case, we have assigned 1.0 and 0.1 respectively to the weights of the connections of first and second neuron. 50 and 30 are the biases assigned respectively. We take the first record, feed the input from the dataset to the network. Based on the data that we have for this record, the expected output is 100. We do the forward pass and calculate the value of the intermediate stage. That is, value after the first neuron. This value is 54 in this case, 4 multiplied by 1 and added with 50. The output from first neuron goes as the input for the second neuron, and based on the weight and the bias, the final value is calculated. Here, we multiply 54 with 0.1 and add it with 30. We now calculate the error based on the computed value and the actual value. Remember, this is called the forward pass stage. Now, freezing the first set of knobs, that is, the weight and the bias on the first neuron, we tweak the values of the weight and the bias in the second neuron. Next, we go one step backwards and tweak the value of the weight and the bias of the first neuron by keeping the weight and the bias of the second neuron frozen. This, you may recall, is called backpass. We repeat the same process all over again by feeding the second record to the network. Please note that we do not reinitialize the weights before picking up the next instance because we do not want to lose the learning from the previous instance. And then we do the same for the third record, and then for fourth. At every stage, the weights and the biases of neurons are fine-tuned based on the difference in the actual and computed errors. When all the records in the dataset have gone through the process, we say that it has completed an epoch. We now start again from the first record. This is called second epoch. Note that we do not reinitialize the weights and bias when we start a new epoch. The weights and the bias from the previous epochs get carried forward to the subsequent epochs. We continue this process as long as the overall error is going down. Once the epochs are completed, we say that we have trained the neural network with our data. We are now ready to predict the salary of a new employee whose number of years of experience is known. Let's extend the use of neural network onto the MNIST dataset. Assume we have an instance of an image of digit 8. The task of the network is to identify the image as one of the 10 digits, 0 to 9, and assign it to the corresponding label. We have 784 pixels in this image. Each pixel is an input to the network, and we have 10 outputs labeled 0 to 9. In such cases where we are doing classification, we want the neural network to give out the possibilities. Here, you can see that the network has predicted the highest probability, that is 0.6, and therefore assigned it to the label 8. Let's understand how this training was done, keeping in mind the same process of forward and backward pass that we saw earlier. Just like the earlier example with two neurons, we initialize the weights and the biases of all the neurons in all layers. As a first step, we take the first instance and then feed the inputs, the pixel values, to the 784 input neurons. The expected output, that is the actual probability of the drawing of digit 8, is 1, while that of other digits is 0. We calculate the intermediate values or probabilities at the second layer based on the weights assigned to the neurons and the biases. And then we calculate the result in the final layer. After the forward pass, we get the computed value for each label and find the error between the computed and the actual probabilities. We now tweak the weights of last layer by freezing the values of weights and biases of the other layers using gradient descent technique. Now we move to the previous layer, in this case the first layer. We tweak the weights and the biases of the first layer, keeping the second layer frozen using gradient descent. Once we are done tweaking the weights and biases of both the layers, we move on to the next instance. In this case, we have shown that we picked 0. Now the pixel values of 0 will be fed to the neural network and the weights will be tweaked further such that the actual values match the predicted values. After the first round of training with all the instances from data, we start the next iteration round from the beginning without resetting the weights and biases. The iteration is also called an epoch. We keep the iteration going as long as the overall error keeps coming down. If the error is no longer going down, we stop iteration. This is how we train a neural network to recognize the images. A similar strategy can be applied to recognize faces and to identify the speech and more. We may not be able to visualize how exactly the neural network is doing the magic or how the weights values impact the outcome. Though we can think of neural network as a whole like an electronic circuit, which is auto-created in order to achieve the desired outcome. The weights, the biases along with the number of layers, number of neurons that are present in each layer, and how neurons are connected defines the architecture of the network.
All right, now that you understand the backpropagation theoretically, I would like to take a bit of more mathematical approach to understand backpropagation. Okay, so essentially, let's define the neuron. Okay, let's define the neuron. Here we have tried to generate the data as we did explain earlier. So there's nothing new here. I just copied the code above. Now let's learn what exactly the neuron is. Okay, neuron essentially is, or let's say neural network. Okay, in the neural network, what we have is these neurons, right? And these are the biases. Bias is nothing but neuron with a single value, fixed value called 1. Okay, and basic idea is that if we connect these neurons together with these edges, for some values of these weights, there would be the best output. Okay, so we got W11, W12, W21, W22. So we got 4 weights. We need to tweak these weights such that the output generated by this neural network is very close to the real. Okay, so we have to come up with those 4 weights which basically give the best results. All right, now in this assembly, what we have is the output of this neuron is this weight multiplied by this value plus this weight. Notice that this value is constant. Okay, this is the input that we are giving and we are asking system to predict an output. Okay, now the next one is this neuron, which has basically the output of this place is going to be W21 multiplied by H1 plus W22. Okay, so this output is the output of the neural network. Now, how far is this output from the reality? How do we calculate that? By the way of saying error equals O1 minus the real value of y and square of it. right? So for this value of x, predicted value by the neural network of y, the predicted value of the y is O1, right? While the actual value is this, so how much is the error? O1 minus y square. Now, what we have to do is we have to minimize this error. We have to minimize this error. So what we're going to do? We're going to do gradient descent on all of these values. We tweak these weights in the ratio of, in the proportion of how much is error impacted by each of them. So we will tweak W1, W11 in the proportion how the error is impacted by W11. Okay? So the main idea will be to compute the impact on error by each of these weights. Alright? So a neuron is nothing but given the W11, the weight of all the edges that are coming in, and given the input value, we will get this return value, right? W11 multiplied by x plus W12, correct? In reality, at every neuron, there will be hundreds of such edges or millions of such edges coming in. So this W is going to be a million. So instead of putting it like arguments to this function, we will be creating an array of these and pass it here, right? So basically, the neuron's value is this, correct? Now, there is something called activation function, and we can talk about it later. Okay, and also we will leave you at this point where you can innovate in creating your own neurons, experiment with them, and see which one is doing better. All right. So this is a very important chapter because this is the whole purpose of the exercise. Okay. Now, we're just defining our very plain simple neuron. Ideally, there is more complex one, but right now, for the sake of simplicity, so that you can understand it, we're just keeping it extremely simple. So at any point of time, the neuron's output is W11, the weight of one edge multiplied by the signal at that end, right? Input value multiplied by the strength of the weight or with strength of the connecting line. Okay, perfect. Now moving ahead, okay, or you can think of it with that example that we gave with the hot water, cold water, right? This knob is connected to the hot water, this knob is connected to the cold water. Okay, and similarly here, and you can notice that at every layer where there is an input, there is a extra bias. This is called bias because this helps us, get better results because it gives one more degree of freedom. All right, so that's our neuron. Now, the forward pass, the overall O1, how do we calculate? The value of the first neuron, first we calculated this, then based on this, we calculated the output of the second neuron. Notice that H1 is being passed instead of X1. So this multiplied by this H1 plus W22, right? That's the output. That's the forward neural network. Now, the overall error is how much? Given something like O1 and given the actual value of Y, it is going to be difference of this and square of this. Also, please note that you can have more kinds of errors, right? But generally, the squared error is more popular. Further, here is the overall error, the function. So it calculates first the value of output, then subtracts it from the actual and gives you the square. And it takes the four weights and it also takes the x and y. Okay, so I hope this one is clear. The neuron forward value computation of the neural network, basically predicting the values, given the weights and the x, it's predicting y. And here what we're doing is predicted value is O1 and we are computing the delta and squaring it, right? This is the error for this input, this actual output, and these weights. Okay, now what we're going to do is, first of all, we're going to assume that these weights are random. Okay, or you can say that we are initializing these weights to be random values, right? We are initializing them to be random values. And then we are moving ahead. Okay, so we're going to iterate over and over, right? And what we're going to do is we are feeding one variable at a time. Usually we feed more inputs at a time, but since there are 100 records in this X, right now we're going to pick one record at a time. Okay? If there were Usually we take a small batch and then do the computation and do the calculation better. But right now we're just feeding one element at a time. That makes our calculation or thinking easier. So we take one value of X and actual value of Y corresponding to that X, right? So this is actually predicted for this one, right? Now we have to find out that neural network which satisfies this, correct? So what we do is we figure out how is error changing with respect to weight 11, right? W11. How is this error changing with respect to this? How is this error changing with respect to this? How is this error changing with respect to this? How is this error changing with respect to W22, right? So that's what we are computing here. Okay, remember that we wrote very generic function called diffp, right, in which we pass the error function first, okay, and remaining arguments last, all the arguments with which this function need to be called, and the second argument tells us with respect to which of these we want to differentiate this function, right? So first we differentiate this function with respect to w11, therefore we have put 0 here, then w22, then w21, w22, like that, right? So basically what we did was we calculated the change in error with respect to each of the weights, correct? And we tweaked all these weights in the same proportion, just like gradient descent, right? So this way we are training the neural network. This way we are training the neural network. All right, let's just try to run it. Okay, let's see if it runs. All right, now here we try to plot it. We ask the neural network to predict the values for all the values of capital X, and it predicted well. And when we plotted the predicted value, this is how it looks like. See that? So this is how it looks like. Okay, one more thing I want to tell you here. Unlike the case of gradient descent above, where there were only M and C that needs to be predicted, here there are 4 values. Therefore, it is not possible to come up with this kind of model. Now, the amazing part about neural networks is that if we use the activation functions here, okay, and use more neurons and similarly more layers, we can have as many hidden layers as we want. Right now we just created one hidden layer and did the calculation for that. In case of the neural network, we can have multiple tabs and more neurons in each layer, and that seems to give wonderful results. So as an assignment, what you do is change this neuron function by putting one activation, right? And try to add more variables here. Try to add one more hidden layer and then see, is it able to solve really complex one? Right now, the data is like this. So in case of scikit-learn, take a look at the data, a little more complex data such as moons, and then try to come up with a model. Try to or let this neural network try to come up with the model that can predict the moons. All right. So this was back propagation. I hope you were able to understand what we discussed. It's pretty simple. I have broken down backpropagation into two parts. This one is the easiest way. The next one I'm going to discuss further. All right. So what we just learned was how the backpropagation works. So this was the simplest way to understand backpropagation. Okay, but there were downsides to it. Okay, the downsides were that every time we are calculating the rate of change of error with respect to a weight, we are calculating this error, right? And if you notice this, on every error calculation, what's happening is the feed-forward neural network is being called twice. One at the value of W, other after increasing tiny bit on the value of W11, right? So on here, this forward neural network is being called how many times? 8 times. Twice here, twice here, twice here, twice here. So it's going to call that neural network twice. So this is inefficient, though there are multiple ways in which things are inefficient, but this is inefficient, and it's not exactly how the backpropagation algorithm was defined, though it's doing exactly the same thing what backpropagation does, but this is a little more inefficient. Okay, so we're going ahead and going to make it more simplified and breakdown so that when we calculate the previous one of these rate of changes, that can be used further. Okay, and that would help you understand exactly what's going on. All right, now let's just move ahead here. Okay, so let's start with backpropagation algorithm again. Initially, we would basically randomly generate these weights. You can think of the example that we discussed earlier as the knobs, right? These are 4 knobs that we need to tweak. Okay, so we know how to calculate the output of a neuron, W11x, W12x, and there will be, of course, right, the activation function is still not there. Okay, we are not going to talk about activation function in this discussion because adding an activation function would just take a moment of time and remaining of the tutorial will remain as such. Okay, so try adding an activation function or trying making it more complex and trying experimenting with it. Okay, try experimenting with it. Now, so this is neuron, this is the squared error, and what we are doing is we're going to run this iteration these many times, 50 times. And here what we are saying is we are picking one record at a time. Okay, so X represents a single record, YY represents a single output. Okay, this is the actual data. Okay, in the forward pass, we basically first calculate H1, right? We know this part that H1 is neuron W11, W12X, correct? X is this one. This is right now assumed basically randomly initialized. Okay, these are randomly initialized. Now this will give us H1. Okay, this will give us H1. Let me just take out that diagram. Okay, this is the diagram, and let me just put it here. Okay, so this is the diagram. So what is it that we are trying to do here? We are trying to go from here till here. So we calculated H1, right? That's the first step, right? And then from H1 we calculated O1. That is the second step, correct? Okay, right? So we calculated H1, then went up to the O1. That's what we are trying to do. Let me go down. Okay, so we calculated H1, then we calculated O1, right? Initially, these numbers are all random, correct? Further, what we do is, now we are calculating the rate of change of O1, rate of change of error with respect to O1, right? Rate of change of error with respect to O1, okay? If you are doing algebraic differentiation, it will come out to be 2 of O1 minus y, but that's not really required, okay? We can just differentiate the Python function, right? We know that part. Okay, so we calculated how is error changing with respect to O1, correct? Then how is O1 changing with respect to W21? How is O1? So we figured out how is error changing with respect to O1, right? Then we figured out how is O1 changing with respect to, not this one, sorry. How is O1 changing with respect to W21, correct? Right? So we calculated this dE by dO1, then we calculated dO1 by dW1 or dW21. So rate of change of error with respect to W21 is this much, correct? How is this calculated? This multiplied by this. Remember the chain rule, right? Remember the chain rule? So dE by dW21 is dE by dW21 is equal to dE by dO1 multiplied by dO1 by dW1. And these two we calculated in this step, right? And this can further be optimized. Right now, let's just try to understand it from this. Then we basically are going to calculate how is error changing with respect to W22. And again, this part dE by dO1 multiplied by dO1 by dW22, correct? Just like previous one. And notice that this one we have already calculated, correct? So we don't need to recalculate this. Okay, so we only need to calculate this, right? So we just saved some amount of calculation. Further, we are saying further, so further we want to find out how is error changing with respect to, how is this error changing with respect to this, right? So what we'll do is how is error changing with respect to O1. Then we will find out how is O1 changing with respect to H1, right? And then we will find out how is H1 changing with respect to W11, right? So if this is A, this is B, this is C, the dE by dW1 is going to be A multiplied by B multiplied by C, correct? That's how it's going to be. Okay, I'm going to delete this and okay, so this is a clean diagram. So I hope you're clear about it. So dE by dW11 is essentially calculated that way. dE by dH, dE by dH, or dH1 you can say, is basically dE by dO1 multiplied by dO1 by dH1. Okay, that's how we have computed here. You can see. So dE by dH or dH1 you can say, this is how we have computed it just like above. Similarly, dH by dW1, which is pretty straightforward, right? We have calculated like this. Okay, dH by dW1, we know that this neuron need to be differentiated with respect to W11, and that's how it is. Further, we are going to calculate W12 in the same fashion, right? Rate of change of error with respect to O1, which we have already calculated. Rate of change of O1 with respect to H1, we calculated in the previous step. And then rate of change of H1 by dW12, that's the only one that we are calculating. So you can see that as we are going forth, the differentiation computation is being utilized from right hand side. That's why it is called back propagation, because if you propagate from the back side, right? So whatever calculation we are using here, they will be used, that whatever calculation we are doing here, they'll be used in the next layer, right? Now, if you think about it, this is one reason why we have to load the entire neural network in the memory, because we need the rightmost layer to calculate the next one, right? Because the rate of change of this one we know, rate of change of this one we know, because we know this part, and rate of change of this one we would only know if we know the previous one. Okay, so that's the way the back propagation works. Once we have calculated rate of change of error with respect to each of the weights, then we can tweak the weights in amount which is proportion to the rate of change of error with respect to each weight, right? Remember this one that we did in gradient descent as well as normal back propagation in the previous step. Okay, and here we go. All right, so this one seems to be unindented properly. Okay, and we can, okay, we have already done this well, so we don't need it. Okay, so that was how we have, okay, so you can see that we have successfully built another backpropagation algorithm, which is way more efficient than the previous one. Probably it'll be around 4 to 5 times or maybe more, it'll be that much efficient. Okay, so here we are plotting it and you can see that this is doing pretty well. This is doing pretty well. And the way we can compare these models is by the way of comparing the errors. Errors on unseen data by the model. All right, so that's pretty much about the backpropagation. I hope this is clear to you. And if it is not clear to you, please put it in the comments and also reach out to us. Okay, so the idea as part of this tutorial was to be able to code the backpropagation, because I believe that if you're able to code something, only then you understand things clearly, right? So if you can code something, that means you really understand it. And hence, this exercise basically walks you through the entire code. And this is mostly, simplified version of the actual algorithm, because actual algorithm becomes very confusing because of all the libraries and functions and so on. Therefore, I tried to make it simplified. All right. Further, there are many things like, for example, there could be many neurons and hence there could be many weights, and hence we cannot have W11, W2, 1, 2 and so on. Instead, we have to deal with arrays. And when we deal with arrays, that's what we call it like linear regression. Though it's not really required to understand linear regression, all you have to understand is how do NumPy arrays work. Okay? And also, please note that most of these calculations happen in a single shot. What I have showed you in a step, one value at a time, in reality, these values happen in a single shot. Okay? Second is that right now we only dealt with one hidden layer, right? This is called the hidden layer. In reality, there would be thousands of hidden layers and there would be some kind of parameter to quickly add or remove the hidden layer, right? In our case, our calculation was very much specific to one hidden layer. But in reality, we have to come up with a code which is very flexible so that it can have any number of layers on the wish. The next one that we already discussed was that the neuron's definition is complex and it generally have activation function, and sometimes there are different kind of neurons. Like for example, in case of recurrent neural network, what we have is basically a line going from the previous one to the neuron like this, right? You can think of W31. Okay, so the output of H1 is W11 multiplied by x plus w12 plus w31 multiplied by O1, right? This is how the RNN looks like. Okay, so with this knowledge that we just discussed, you are not only capable of coding a backpropagation, but also you will be able to innovate and probably come up with your own neural networks. All right, I hope I was able to add some value to your life, and have a great day. Happy learning. Thank you.